Hello, this is Skylar Mitchell. I'm going to be doing my final presentation for Math 614 Algebraic Reasoning. And the topic for my presentation will be exploring the connections between algebra and geometry. So, to begin exploring what connections there are between algebra and geometry, we first need to define what each field encompasses. So first, what is algebra? Algebra is a branch of mathematics that generalizes arithmetic into symbolic language, and it can be applied more broadly and abstractly, which offers a systematic approach to problem solving. Its emphasis on deduction through symbolic manipulation establishes a systematic toolkit applicable across scientific domains. And really, algebra's power emerges through detecting meaningful patterns and creating rules for those patterns. And so oftentimes algebra is viewed as highly mechanical because of its computational and procedural nature. Next, geometry is the field in which it deals with spatial properties and relationships which explore the visually compelling properties of shapes and spaces, making the abstract tangible. Geometry, along with algebra, is one of the oldest branches of mathematics. Its meaning comes from the etymology of the two Greek words that make it up, which means earth, and metron, which means measure, so literally meaning earth measuring. Overall, geometry lends visual insight and intuitive qualities to enrich mathematics. It can offer these qualities to algebra if we notice the intersection and overlap between the two, which is going to be the focus of this research. And lastly, geometry really is viewed as highly visual and embodied in nature. And so we will see how these two fields relate. So one of the most well understood illustrations of the close relationship between the two is seen with the 2D Cartesian coordinate system, where algebraic equations in one or two variables can be interpreted as lines, curves, and shapes in the plane. So ultimately, algebra is often seen as separate from geometry. Algebra is concerned sometimes, in this source it says, with manipulation in time, whereas geometry is concerned with space. And so this quote says, these are two orthogonal aspects of the world, and they represent two different points of view in mathematics. And thus the argument or dialogue between mathematicians in the past about relative importance of geometry and algebra represents something very, very fundamental. And so the analysis of these two core mathematical branches exposes some of the meaningful connections between algebra and geometry. And we can see how we can share between the two to make them more meaningful. And so the inseparable nature of algebra and geometry shows exactly how the two fields cannot be separated in terms of how they are taught. Quinto argues, presenting the relationship between geometry and algebra as a dichotomy is something of an oversimplification, arguing that algebraic geometric contrast, so far from being a dichotomy, actually represents something more like a spectrum, um, where there's it's a spectrum. There's a lot of overlap between the two. The research indicates that students learn better when perceptual understanding is at the heart of mathematics, and math is made meaningful through representations, where tasks are focused on realism, and there's a great deal of research exploring the role of visualization, which I would like to summarize in this research. So, some ways in which we can see algebra and geometry already being utilized as a merger and where they are melded together is first analytic geometry, which is blending algebraic and geometric techniques by representing geometric shapes through equations. Then we have calculus, which can be seen as the intersection between algebra and geometry because it relies on algebraic manipulation and geometric reasoning. More specifically, we have vector calculus, which is more geometrically focused. There's also linear algebra, which deals with the study of vectors and projections. And geometry has been often presented in teaching and learning the subject. We also have algebraic topology, which uses algebraic invariants to distinguish topological spaces. We also have geometric group theory, which studies finitely generated groups via geometric representations. We also have geometric algebra, which is often called Clifford algebra. And it's the manipulation of geometrical objects such as vectors, and it's a little more complicated than that. But one branch of that is geometric calculus, which involves more of the calculus side of differentiation and integration. And there's also what's known as the Langlard's program, which is a set of conjectures and connections between algebraic number theory and analytic aspects of geometry. So how do we see this geometry in education? We see that there's a steady decrease over time, actually, in the teaching of geometry in schools. This is researched by Falker in 1986, talks about the decrease over a span of over 50 years, seeing that gradual decrease. Barnes in 2003 researched how that impacts the students later in their education and found that students seem to have limited visualization and spatial reasoning skills. And so there can be an argument made for a increase in geometry in education. And more than that, what I would argue is seeing a intentionality in how the conversation between algebra and geometry is not seen as separate, but melded together. And so one way we can do that is using visuals in mathematics. As stated by the National Council of Teachers of Mathematics in the United States, representations are necessary for students to understand mathematical concepts. They allow students to recognize connections among related concepts and apply mathematics to problem solutions. And so why use visuals in mathematics? A quote from Bishop in 1989 says, "A visual image not only organizes the data at hand in meaningful structures, but is also an important factor guiding the analytic development of a solution." The goal of mathematics education is no longer as computationally driven. Research has shown, but there's a shift towards a focus on problem solving as opposed to computational, mainly because we see that with the fast production of correct computers and technology making precise and more efficient calculations. This leads to this shift towards the problem solving and conceptual side of mathematics. Instructional content should then incorporate diverse representations of mathematical ideas, and students should be given opportunities to link these representations together. Regardless of their focus, most papers that aim to discuss the role of visualization in mathematics, nearly all of them depict a similar picture where a mathematician's success is owed largely to his or her visualization skills. So while early mathematicians leaned heavily on visuals to prove or establish the existence of mathematical object, those in the 19th and 20th century reduced the use of visualizations, and this change has resulted in a shift of focus for researchers to determine the significance of visualization in mathematics. So, again, why are we using representations? One study by Elizabeth Finema explores the importance of the varieties of models used in mathematics. So she concluded that there is a lack of agreement in understanding the role that concrete and symbolic models can and should play in facilitating learners of mathematics. And so in the study, she goes into explaining concrete models are those that come from directly manipulating something. So in this case, maybe there are 4 groups of 3 in each group. We're actually manipulating some kind of objects. Maybe that could be popsicle sticks or something similar. And so the meaning comes through that manipulation of the objects. She also discussed symbolic models, meaning being pulled from the use of symbols, and the meaning that is made is determined on the meaning that an individual has placed with those symbols. And so we can see this with the same example of 3 plus 3 plus 3 plus 3 equals 12. Looking at the symbols being the 3, the plus, equals, and 12 are merely marks which suggest arbitrary Trojan symbols that are used to relate the relationship of what's actually happening in that scenario. And so Finema concluded in this research that the data indicates that an important factor in whether representational models being utilized are the most effective or not is whether they are suited to the development level of the learner. So if a student is more in the elementary range, they're going to rely more on the concrete methods of modeling, with a shift seen as the more that a student gets towards high school level, there's a shift towards that favors the symbolic representations, because oftentimes the concrete models just don't help students in problem solving abstractly as much as the concrete. The learning of mathematical ideas is likely to be facilitated by a predominance of concrete models in early grades, again, gradually increasing in later grades. And she clarifies that if children are given freedom, they will select the model that makes the idea most meaningful to them. And so ultimately, if concrete and symbolic models are used in a fluid and blended way, meaningful learning of mathematical ideas is more likely. So now that we have established why visualization is important in mathematics, I wanted to discuss another study that discusses visualization as it relates to geometry. In this report, there was a focus on some aspects of the nature, the role of visualization and imagery in the teaching and learning of mathematics, particularly looking at what's called geometrical reasoning. So Duvall suggests that geometrical reasoning involves three kinds of cognitive processes. First is visualization process, which is the visual representation of a geometrical statement. Secondly is construction process, which is using tools. And then lastly, there's like the reasoning process, where there's some discourse for examining knowledge and explaining that knowledge, oftentimes which is used in proofs in geometry. And so Duvall argues that these are the three kinds of cognitive processes that are closely connected, and their synergy is cognitively necessary for proficiency in geometry. And so I want to discuss how we can link algebra and geometry through visualization. We just saw here that in this diagram, this is how at least one study understood the relation of visualization and geometry, going from visualization to reasoning, construction, which these arrows showing the way in which those relate. So ultimately, how does that lead into algebra as well? So how do we link algebra and geometry through visualization? So first I wanted to talk about some of the ways in which to make this more concrete. We see visualization in algebra and geometry, specifically in those fields of study. So first in algebra, we can see while solving text problems by equation method that uses visualization, also while studying various types of functions, and by means of showing functional connections between different types of values, analytically, in tables, graphically. And then on the other side of it, we see this in geometry while solving problems by the test of equality and similarity of triangles, trigonometric functions, and methods of coordinates and vectors. So each of these has many different visual centric studies within their field. And so that's going to be relevant to us as we try to further understand visual as it relates to the two fields. And so to get a better grasp of this, I wanted to look at this idea of visual reasoning. So I underlined this here because this is not the same as visualization, which is involved in this process, but it makes a clear distinction between visualization and this process called visual reasoning. And so this is a more generalized framework of the exact example we saw with Duvall and the triangle diagram, talking about the different phases of this process of visual reasoning. So that one was more, Duvall's was more focused on geometry specifically. This is more generalized, that can be applied to both, and really we can see the same kind of steps from this, starting with visual representation doing. That comes first. That's where it all starts. Visual representations can be used in the solution of a problem or in the process of understanding a concept. And so then after that, visualization takes over. Basically an individual interacts with the visual representation that he or she has created and is presented to the next stage. So then we got transitioning to mathematical thinking, where they are specializing, generalizing, conjecturing, and so on. And at any of these points with the arrows in this diagram going on the sides, that is where during these activities the individual can return to a previous stage and also be involved in other processes. So it's not necessarily as simplistic as it may seem. It's a little complex in how a person thinks through and visually reasons through different math problems. And so how can we see this in algebra? So we talked about geometry. I wanted to look at some different studies of how visual representations give meaning to algebraic concepts. So this first one is a study by Marx. A quote from it is, "Perception is not an obstacle to abstraction. On the contrary, culturally regimented perception is the engine of expert mathematical reasoning. In particular, high-level algebraic reasoning is accomplished by basic perceptual processes that are adapted to reflect abstract conceptual knowledge. Difficult conceptual tasks are thus transformed into robust perceptual ones. This exemplifies a strategy that recurs throughout human cognition. Perception and action are rigged up so that the senses have therefore become directly in their practice theoreticians." Another study by Unal, the results of this study revealed that the use of algebraic visuals as opposed to arithmetic visuals was associated with enhanced algebraic reasoning. So further, although the students initially relied on standard algorithms to explain equations and inequalities, they could produce accurate algebraic visual representations when prompted. These findings suggest that students have multiple representations of equations and inequalities, but only express visual representations when asked to do so. In keeping with the general relationship between visuospatial abilities and mathematics, self-generated algebraic visual representations particularly mediated the relation between overall mathematics achievement and algebraic reasoning. And then lastly, a study by Leakin, Rosa Leakin, from a visual to symbolic object in algebra and geometry, study with mathematically excelling male adolescents. This study explores how to make the invisible of mathematics visible. So Lycan and co-authors performed a comparative analysis of brain activity associated with transition from visual objects to symbolic objects in algebra and geometry. And so Lycan concluded from that geometric task increases the participant's working memory load by keeping the visual geometric object in working memory until the problem is solved. And so in that example specifically, that dipped in a little with geometry, but this conversation of how we get from visual objects to symbolic is a very important narrative that I think is very important from the research. And so I wanted at this point to look at some case studies for ways of linking algebra and geometry. So we're going to look at some specific examples of the two subjects in harmony. So ways of linking algebra and geometry. First is a case for GeoGebra. I found a study where it talked about GeoGebra being utilized, which is a computer software that is an open source website, and basically I wanted to explain GeoGebra and why it is so important by breaking it down into the two prominent forms of software for visualization and understanding mathematics. So first, there's this CAS, which is a computer algebra system, and this is what focuses on manipulation of symbolic expression. Then we also have DGS, which is meaning dynamic geometric software, which concentrates on relationships between points, lines, and circles. So these are two separate types of systems that, when computer systems were first created along these lines, there was sort of a division, but GeoGebra is special. It provides a closer connection between the symbolic manipulation and visualization capabilities of CAS and the dynamic changeability of DGS by providing not only the functionality of DGS, but also of CAS. So you get to see the work with points, vectors, and segment lines and conic sections like you see with geometry, but there's also the equation side and the coordinates, and those can be entered directly, and functions can then be seen. You have two windows in the software, and so you have the algebraically defined window and then the more visual window. So since the writing of this article, there have been many other softwares that also achieve this similar purpose. Another method that we can see successfully merging algebra and geometry is virtual algebra tiles. So the virtual algebra tiles resource in this specific study allows users to represent models through manipulation of geometric figures. And so this one I found was online, but you could also use just algebra tiles in general to achieve the same purpose. In this specific study, the participants were about 40 students of engineering degrees who were randomly assigned to experimental or control groups. And the results indicated that the system has a large effect size on learning effectiveness and a promising long-term knowledge retention. Students concluded that this version of algebra tiles is more motivating than other versions because it is presented in a format that stands natural to them. So students felt more comfortable in the virtual environment, and so the learning process was very effective in this study. And so ultimately, by looking at exploring algebra tiles, together with deliberate procedural and conceptual variation, I think the research shows that it can make algebra more meaningful and conceptual and really less cognitively overloading. So here's some more case studies for ways of linking algebra and geometry, just continuing in this same line of thinking. I wanted to look specifically at quadratics and area models in these different studies that I've found. The first study is on representing quadratic functions. The union, again, we're looking at is how algebra and geometry are connected. So the purpose of this study was to investigate geometric contexts of measurement involving quadratics, their functional relationship, this study was concerning algebraic thinking, and it focuses on describing the functional thinking exhibited by sixth grade students enrolled in curricular enhancement programs. the students were asked to calculate the areas of certain figures, for which some of the data were given and asked to formulate general rules. So here to the right, you can see figure 1 and figure 2. These were part of the questions that were asked of them as related to these two images. And so here was a task. A smaller square in the upper right corner was removed from a square with sides measuring 6. We asked students to determine the relationship between the area of the resulting figure and the side of the corner removed, which was 36 minus S2, or side 2, where the area AS was the area of the resulting figure and S was the side of the corner removed. And so over to the right, you can see there's a table summarizing different things here that we'll get into. First off, the study acknowledged different types of representations. Each type included verbal language, algebraic symbolism, and numerical symbolism. And so the results show that over to the right that there are different types of representations used in each of these two tasks. There was session 1, which was problems 7 through 13, and then there was session 2, which was problems 14 through 25. And so what they've done in this table is they're analyzing what kind of responses these students came up with. Were they no answer? Were they verbal? Were they pictorial? Were they symbolic? Or were there multiple types of representations? So as you can see here, there's many of these that had verbal, and also many of these had multiple, and some of them symbolic. The results ultimately showed us that the student's potential to express generalization through multiple representations, mainly verbal and symbolic. So a main focus there, seeing a lot of verbal and symbolic. And their versatility in showing different representations, multiple different representations, is proof of their generalization process, despite there maybe being some errors in their mathematics. And so ultimately, for example, the students overcame the difficulties through their use of those verbal or multiple representations. And so again, just to be focused into the point, participants in this study had difficulties expressing structures involving quadratic functions, but they were able to overcome that, and they displayed the potential to use different types of representations to establish the functional relationship. The next study I wanted to talk about is concerning area models. This is where pre-service teachers were assessed in their ability to link fractions and geometric measurements. The purpose was it was determined that the results showing that pre-service teachers' use of area models in this cake problem illustrated at the bottom demonstrated their different levels of sophistication. So they were checking the different levels there of their sophistication in understanding fractions and geometric concepts. And their study found that it indicated that 88% of pre-service teachers had relatively low GMK, which means geometric measure of knowledge, or FK, which means the fraction knowledge. in that they exhibited some errors in the use of area models to solve the problem. So why is this important? Well, it gives us some insight for improvement. Some of the successful strategies, the analysis of it came with counting the number of square units and decomposing the shape to find the areas. So those were two successful strategies that could be used. How do we apply this in creating similar tasks can be important as we talk about the relation between algebra and geometry coming together. Some different ways that are important to keep in mind is utilizing well-designed atypical visual representations could encourage mathematicians to examine their own preconceptions and focus more on the meaning of mathematical concepts. This is going to be important when trying to blend algebra and geometry concepts. Tasks should also purposefully integrate multiple domains of mathematics. So talking about algebra and geometry with giving them multiple entry points to problems. So not necessarily relying on one way of doing something. Next, there's a study on 6th grade students. The purpose of this study was to portray students' misconceptions and errors while solving conceptually and procedurally oriented tasks involving length, area, and volume. This study, among other studies cited within this one, concluded that the students of this study had serious difficulties in truly understanding and applying the concepts and skills involved in area measurement. Their inability to grasp the spatial structure of the multiplicative structure and inability to converse in area and superficial understanding of length measurements all resulted in the above mentioned errors, and similar errors were observed concerning calculating volume. So how does this lead us into insight for improving the misconceptions that we see? There should be an appropriate balance between conceptually dominated, this notion of thinking in a second dimension for the concept area. So a balance between conceptually dominated and procedurally dominated, talking about calculating the area of geometrical shapes, those two learning objectives. So again, this goes back to our conversation of blending algebra and geometry, that this research itself indicated that it is important to keep a balance between conceptual and procedurally dominated learning objectives. Also, measurement content should also be focused on the interrelations of variety of measurements. So for example, this is how length, width, and height produce volume and their relationship between perimeter and area, things like that. Inquiry-oriented teaching materials may also enhance measurement instruction. For instance, ruler construction activities might be designed to help students explore the structure of the ruler before they actually use a ruler and have misconceptions with that, is one of the examples we could see in this study. And so, in conclusion, the findings of this study revealed a wide range of misconceptions and errors that the 6th graders had while solving conceptually and procedurally oriented tasks on spatial measurement. And this might be considered one of the valuable contributions to removing the barriers of students' learning of measurement. Another study seeking out to deepen student understanding of area and volume using unit and arrays had students of all ages, or had students in this case look at our different, specifically, we'll get into, they talked about using it like area, volume, and units in certain contexts. But anyway, the studies that were used with elementary and middle kids saw that there are some issues with how they were conceptualizing area, and so it had a lot to do with them not understanding when we're looking at arrays. Those units are what you were counting, and so they would instead kind of leave holes, whether because of misunderstanding the nature of like 2 dimensions versus 3 dimensions, or any other number of ways. And so students of all ages can have difficulty understanding these units and arrays as tool for problem solving, and even those who carry out computations accurately may not have a rich understanding, this study showed in the article. But students who do understand arrays tend to be successful with area and volume computations. So thinking about arrays makes it easier for students to understand why area is in units squared and volume is in units cubed. So understanding the nature of that and the why behind that. And so some of the issues usually persist if seen in earlier in their career in school, that persists into undergraduate years. And so there was a study done based off this information, and they wanted to look at the basic area and volume computational skills of calculus students. And so what they found was quite interesting. 73% of students gave an incorrect unit for at least one task. We found that, or they found that students struggled with computing volumes, and so some students computed surface area instead of volume, and others created formulas that constrained both surface area and volume elements. So we can see over to the right here, we have some different categories where some of them there was no surface area element. Some of them combined the elements of surface area and volume. Others only had elements of surface area, or maybe there's some other example here. But ultimately, by looking at this, it calls for a need for using arrays to have some sort of visualization and leading to visual reasoning based off of those visuals to make more sense of these different formulas. Perhaps the issue with the students here is what we notice is that they were not making the appropriate connections between the visual side of the shapes that they envisioned with the correct notation and algebra with it. So, for example, some students would calculate the base and the top part of the volume in cases where that is not required when concerning the volume. And so what are some implications from all of this? in summary of what we've talked about from this research. Post-secondary schools, fields such as linear algebra, will become more successful if there's a shift towards emphasizing the blended nature of algebra and geometry. We saw this with this previous study that ultimately students were not prepared with a blended view of algebra and geometry, and therefore they ran into conceptual errors where there were some holes in their understanding, linking the algebra of computing volumes and the visual nature and the conceptual side of that. And so ultimately, even though geometry is seen as a mere application of linear algebra, many mathematicians believe that by learning geometry, students are better able to understand linear algebra, and they develop what's called a geometrical intuition to visualize problems. This article that is by Dunlap details how France uses the study of geometry and geometric intuition in teaching and learning linear algebra. And the article examines Fishman's work on intuition in science and mathematics using geometry and linear algebra textbooks, and investigates the possibilities and limitations there are in doing this. The relationships between students learning in graphical representations in the context of linear independence. In that context, he says geometric representations in the presence of algebraic and arithmetic modes appear to help learners begin to consider the diverse representational aspects of a conceptual flexibility. There's also a study by Henna et al. Using Thal's 3 worlds, revealing that the visual approach presented in lectures gave meaning to the symbolic world calculations and helped students to gain understanding. And so ultimately, in conclusion, wrapping everything into one narrative, the union of algebra and geometry is seen by extracting the visualization and reasoning processes of geometry and applying these ideas in harmony with the abstract nature of algebra. And so in this way, mathematicians will become more equipped to be adept problem solvers, having a broader perspective of the interweavings of theoretically algebraic and perceptible geometric and their practical, or those perspectives and their practical applications. And so these connections reveal mathematics and mathematicians' coherence as a science seeking to decode the universe's patterns through interlocking abstractions embodied in its foundational disciplines. Thank you for your time and listening to this final presentation. Here are the sources that I used. And so hopefully we can see a emphasis in our education system on blending algebra and geometry and the ways in which we think about those separate subjects. Thank you.